So that's going to cause a torque. Whatever I explained in the previous slide, going to generate a torque which will make the pointer move. The pointer will start, it was at this position. Due to the torque generated earlier, the pointer will move to the position of reading. Before that, I talk about controlling torque, because there must be a control torque which will control the movement of the pointer or the deflection of the pointer. That's called TC, the controlling torque. Controlling torque is equal to K into theta, where K is the control spring constant. It's the spring constant, the spring which I mentioned earlier. We said the rotation will be attached, or the rotor will be attached to spring which will store energy in it while the pointer is moving. So now that spring having a constant, the constant is given as a K, and theta will be the result of this operation. Means when the pointer is starting from here, it's going to stop here, so the result will be theta. So this is the theta we are talking about. Okay, why we care about this equation? Because the pointer will stop. The pointer will stop when TC equal to TC means T control, the control torque equal to the deflection torque. When the control torque equal to the deflection torque, the pointer will stop. The result of that will be theta. So the result of this equation will be theta. So that's going to cause theta generated out of this equation. Example on the torque generated. He's saying here a PMMC instrument with 100 turn coil has magnetic flux density in the air gap of B equal to 0.2 Tesla. So we have a coil. Usually the coil is having this shape, rectangular shape with two sides. It's a coil. So this is the current, and the current going to go out. So the number of turns here are 100. Here, these turns are 100 turns. That's one thing. The other thing, he said this coil is located in a magnetic field. Sorry, let me put it as a yellow. The magnetic field, this one, which generated by the permanent magnet, having the flux, the magnetic field density or the flux density of 0.2 Tesla. 0.2 Tesla. The coil dimension D equal to 1 and L equal to 1.5, which means regardless of what is D and what is L, but he mean by D is the depth. So this is the depth and this is the length. Regardless of that, it's no problem. This is 1.5 centimeter, let's say, and this is 1 centimeter. Though my drawing is not giving the right dimension, but I hope you catch it. So whatever it is, I don't mind. I just want to know that one side is 1 centimeter and one side is 1.5 centimeter. Calculate the torque on the coil for the current of 1 milliampere. It means here, if a current flowing in the coil, if this is the current flowing in the coil, just now I told you this is the coil. If the current flowing in the coil here equal to 1 milliampere, what is the generated torque? Remember that this torque which will carry the pointer to the position of measurement. Again, this is the scale. The pointer used to be at 0. So whenever the 1 milliampere goes inside, when the 1 milliampere goes to the coil, the pointer will move to a new location. So I need torque to carry the pointer from this point to this point. This is the torque we are calculating. We call it TD, deflection torque. So I think in terms of calculation is something simple. It's equal to B into L into I into A into D, where it's equal to 0.5 Tesla into 1.5 into 10 to the power minus 2, because the L supposed to be in meter. This one, it's given in centimeter. We will put it in meter, so we multiply it into 10 to the power minus 2. Similarly, for the depth, it's to be expressed in meter, so it's 1 into 10 to the power minus 2 again, multiplied into N, the number of turn, multiplied into the current I. This is the current. So when we multiply or when we calculate this, we are going to find that TD equal to 3 into 10 to the power minus 6 in Newton meter, or 3 micronewton meter. Another example here. This example, I like to put picture from time to time to get you clear about the operation. So these pictures will help you to be more clear about the operation. So it's the same structure, the same pointer, the same system, but this is given here to make you clearer. And hopefully I will be able to make you even more clear about this. Let us read the question first. He said a moving coil instrument has the data of this one. Number of 10 equal to 100. He mean this number of 10. This coil here, it's having a number of 10 of 100. 100 means 1, 2, 3, 4 until 100. Width of the coil is a 20 millimeter. Depth is 300 millimeter. As I told you, this is not a problem. Whether he call it length or depth or width, we have two dimensions. We have this side, and this side. So we need to get both. One of them is a 20 millimeter, the other is 30 millimeter. Remember that these length to be expressed in meter in the equation. The equation will accept them in meter. The flux density in the gap is equal to 0.1 Weber per meter square. Okay, calculate the deflection torque. It's very similar to the previous example. He wants the deflection torque when the current flowing is 10 milliampere. And after that, he said the deflection angle, he wants to know theta now. If control spring constant, you remember K, the spring constant, equal to 2 into 10 to the power minus 6 in Newton meter per degree. Let us catch the idea here, my dears. He is saying here that if a current flowing here is 10 milliampere flowing to this coil, where the coil is having 100 turn, okay, and the flux due to the permanent magnet here, let me put the flux in yellow. This is flux due to the permanent magnet is equal to 0.1 Tesla or 0.1 Weber per meter square. The dimension of the coil is given here. If all these parameters given, what is the torque and what is the angle? So he wants to know if this is the meter. Originally, before the application of this current, the pointer was here. So he wants to know what is the result angle here, because before operation it was here, after operation it becomes here. So the result will be this angle. I hope now you are clearer about the PMMC. So in terms of calculation, it's similar like before. We are going to calculate 0.1 into 30 into 10 to the power minus 3. Why 10 to the power minus 3? Because as I told you, the equation will not accept the length in millimeter. It's supposed to be in centimeter. So to convert, it's supposed to be in meter. So to convert millimeter to meter, 30 millimeter will become 30 into 10 to the power minus 3. Similarly, 20 millimeter will be 20 into 10 to the power minus 3. This is the number of 10, and this is the current. 10 milli, it's supposed to be in ampere, so 10 into 10 to the power minus 3 ampere. When we calculate all of them, we are going to find that the torque generated, when I say torque or the force, is the same thing. It's equal to 6 into 10 to the power minus 5. So this is now the deflection torque. As I mentioned earlier, the pointer will stop when deflection torque equal to the control torque. When deflection torque equal to the control torque. That's why I am going to consider this equation now. Deflection or control torque is equal to K into theta. That means K into theta equal to this value. That's the idea. So when K theta equal to this value, let me write it. K into theta equal to 6 into 10 to the power minus 5. Whenever I reach to this equation, when I reach to this position, the pointer will stop. So what will be the result? The result will be theta, where theta is equal to this value over k, which 6 into 10 to the power minus 5 divided by 2 into 10 to the power minus 6, which the spring constant. So when we solve this one, we will find that the result equation is 30 degree. The result angle. The result angle is 30 degree, which means the pointer will be deflected by 30 degree. Again, the pointer position, this is the scale, the pointer position originally was here. When we start the operation, the pointer get to be here. What is the result? Is this angle, which equal to 30 degree. After discussing the PMMC, now let us start with the meters, which employing the PMMC. The first one we are going to go through is the galvanometer. Galvanometer is basically PMMC. It's measuring the current in which very small value. Usually it's a scale in microampere, as you can see here. It's used in most of the time to detect whether there is a current or not, to detect the balance condition. If you remember when we talk about the Wheatstone bridge, when we check whether the bridge is balanced or not, we used to use the galvanometer, where the galvanometer is used to detect whether there is a current or not, to make sure that the bridge is balanced. If you notice also one more thing about the galvanometer, that its pointer is pointing at 0, which in the center, and it can measure in both directions, to the left or to the right. Usually its scale comes in microampere. DC ammeter used the PMMC through a circuit. Actually, there will be a circuit. We will do it to convert the PMMC or the galvanometer to a meter. Before I do this, before we go to the construction of the DC ammeter, let us get something about the ammeter. That the ammeter is the device which used to measure the current. Usually it's connected in series with the circuit to be measured. If you notice here, the current flowing in this circuit will go through the ammeter and back to the circuit. So it's connected in series with the circuit to be measured. That's the ammeter. Now, if I want to measure large current with the ammeter, remember the PMMC cannot measure a large current. To measure a large current, we will connect a resistor in parallel with the PMMC. Let us see this in the construction of the ammeter in the next slide. So in the ammeter, as I mentioned just now, we will connect a resistor in parallel with the PMMC, which we call it shunt resistance, or we call it the shunt, RS. It's a resistance to be connected in parallel with the PMMC to take majority of the current through it, and the small current will go to the PMMC. In this case, we will be able to measure high current by the PMMC. So here is the circuit, or the construction of the circuit of the ammeter. The ammeter, as you see, starting from this point and this point. So if I want to clarify this point to you, this is the ammeter, where this terminal and this terminal are this one and this one. See, I will make this dark blue, and here is the same. Now inside we are going to have a PMMC, where the PMMC has resistance and ideal PMMC. So this is the PMMC. We cannot leave it like this, because if we leave it like this, the high current will destroy the PMMC. That's why we connect our shunt here. So whenever we are measuring current from the external circuit, current will go in and it will be splitted. Part will go to the shunt resistance and the other will go to the PMMC. Here, the PMMC, as I show you here, is expressed as ideal PMMC with resistance in series with it. So this is the resistance of the coil. Remember the moving coil? This is its resistance, or this resistance representing the moving coil. It's having a value of Rm. Rm means the moving coil resistance. Now, how to calculate the value of the resistance? How to calculate the resistance value, which will convert the PMMC to ammeter Here is the derivation. Derivation is very simple. We are having R shunt equal to V shunt equal to Vm. He mean this voltage, the voltage on this resistance is equal to the voltage on this branch. It's very logic. Now, if I will express them in terms of current, I will find that IR here is equal to IR here. So I shunt R shunt equal to IMRM. Let us calculate or rearrange the equation to calculate R shunt. We will find that R shunt equal to IMRM over I shunt, where I shunt by itself is equal to 1 minus IM. Remember, this is I shunt to understand what's happening. This is I shunt here. This is I, and this is IM. So I shunt, this current, according to Kirchhoff current law, I shunt is equal to this current minus this current. So if I substitute this value here, we will find that R shunt, this resistance here, is to be calculated as a IM into RM, IM into RM, divided by I minus IM, divided by here, I minus IM. So that's how we can evaluate the value of the shunt resistance to get the ammeter to measure the value we like. Let me just give you some idea about what is the parameter of the equation. The equation parameter are, this is R shunt, which the resistance which we will connect in parallel with the PMMC to measure higher current. IM is the current limit of the PMMC, means the maximum current can be measured by the PMMC. RM is the resistance of the PMMC. Then I is the current which going to enter the ammeter, the current which we will be able to measure. I mean, the maximum current can be measured by the ammeter. It's I, where IM is the current going to the PMMC, as I mentioned in the denominator there. So that's how the equation going to look like. This is going to help you to answer the question after that. Example on the ammeter. An ammeter has, as shown in the figure, has a PMMC instrument with a coil Rm equal to 99 ohm. This is 99 ohm. Full scale deflection of 0.1 ampere. FSD means for full scale deflection equal to 0.1 milliampere. He means here the current needed for the PMMC to go to the full scale. Full scale means this is the range starting from 0 to maximum. The current needed to make this one at full scale is equal to 0.1 milliampere. Rs equal to 1 ohm, this resistance equal to 1 ohm. He asked us to calculate the current passing through the ammeter, means this current. This is the current entering to the ammeter. At what time? At full scale deflection. That means when this is pointing full scale. He's not asking for this current. This is the full scale current for the PMMC. When this current come here, that's what he means. When this current come here, means the full scale deflection goes to the PMMC. What is the full scale deflection to the ammeter? The maximum current entering to the ammeter. So how to calculate it? We will see in the next slide. And here 50% of the full scale deflection, or 0.5 of full scale deflection, and 0.25. So notice here, at full scale deflection, Vm equal to IMRM. Remember, this is Rm, this is the PMMC. Here is R. Remember that this is 99, and the current here is 0.1 milliampere. So if I want to calculate the voltage between this point to this point, it's equal to this current into this resistance. You see, 0.1 into 99, which equal to a certain value not given yet. No problem. I and ISRS equal to Vm. Also, he's saying this current, IS or I shunt. We write it IS or I shunt, RS or R shunt. This current into this resistance equal to the same value. So he want to say here that, if I can write it here, he's saying that 0.1 milli into 99 is equal to this value, IS RS. Remember that RS is known to me. RS is known, so I can rearrange the equation to calculate IS. So IS from here can be found as 9.9 milliampere. So this current here is 9.9. Let me select the right color. This one is 9.9 and this is 0.1. This is 9.9 and this is 0.1. So what is the current here? It's going to be the total, which equal to 10 milliampere. Total, because IS plus IM. IS plus IM is equal to the total current. That means here, the meaning of full scale deflection now, 10 milliampere will enter from here, which will result in 0.1 milliampere comes here to make the pointer at the full scale. That means that 10 milliampere is known as the full scale deflection of the ammeter, and 0.1 milli is the full scale deflection of the PMMC. How about 0.5 full scale deflection? The only thing we will allow 50% of the current to go to the PMMC. So PMMC is 0.1 milliampere. We will take half of it. So we will get 0.05 milliampere. And we will repeat the same thing as before. You will find that the total current at the input of the ammeter, again, let me repeat it. This current will be equal to equal to 5 milliampere. According to his calculation, this current is 0.05 and this current is equal to 4.95. Their total is equal to 5 milliampere. Same thing with the 0.25 of the full scale deflection. We are going to allow 0.25 of the current to the PMMC. So 0.25 of the PMMC current equal to this much. Then after that, we are going to calculate the voltage Vm. We know that Vm equal to ImRm, which equal to the current into the resistance of the PMMC, equal to this voltage. Now from this voltage, we will be able to calculate the current in the shunt. I shunt equal to this voltage divided by R shunt, which found to be this much. Now this current and this current are together coming from the input. Again, to make the things clear for you, just now we calculate the current here is 0.025. The current here is 2.547 all milliampere. Both of them are coming from here, which found to be 0.5 milliampere. Let us consider this other example on the ammeter. In this example, he's saying a PMMC instrument has a full scale deflection of 100 microampere and the coil resistance of 1 kilo ohm. Coil resistance 1 kilo ohm and the PMMC. This is the PMMC, where, as he said, the current here is 100 microampere and the resistor here is 1 kilo ohm. Now he's saying calculate the required shunt resistance. We need to calculate the value of this resistance, which allow us to measure a current of 100 milliampere. I think from the previous question, we understand now that this is the current which to be measured. So how are we going to calculate this question? Simply, we are going to calculate Vm. We will calculate Vm between these 2 points. Then, after calculating Vm, I will calculate Is. Then Vm over Is is equal to R shunt. How he did it? To calculate Vm, it's equal to ImRm, which equal to 100 millivolt. Now I is equal to Is plus I shunt, means this current here, this current equal to this current plus this current, which means if I want to calculate this current, which Is, it's equal to I minus Im. So Is is equal to I minus Im, which equal to 100 milliampere minus 100 microampere equal to 99.9 milliampere. Now if I know the current, now what I calculated so far, I calculated the resistance here, the current in the resistance, we calculated this value, and the voltage on the same resistance. Let me draw it again. This is the PMMC. So just now, what I calculate this current, which found to be 99.9 milliampere, and earlier we calculate this voltage, which found to be 100 millivolt. That voltage is the voltage of this resistance, also because they are in parallel, as you see. So the voltage over the resistance, not the resistance, the voltage over the current, the voltage here, Vm over Is, is equal to Rs. That's what he did here. Rs equal to Vm over Is is equal to 1.001 ohm. My dears, here don't approximate, please. Don't approximate. Keep the value as it is. If you have very long number, keep at least 4 digits after the decimal point. At least keep 4 digits after the decimal point. So 1, 2, 3, and the 4. Okay, don't approximate, though the number can be approximated, but don't approximate because this is kind of precise calculation. For the other part, you want to measure a current of 1 ampere. Let me again repeat the circuit. The circuit is something like this. This is the PMMC. And here we are having a resistance, which we don't know its value. We need to calculate the value of this resistance, which allowing us to measure a current here of 1 ampere. Now I hope the idea is clear. We are going to do the same thing as before. This resistance is known to me. I know the value of this resistance. I know this resistance. So this current into this resistance will give me Vm. That's the style always. So this is Vm. Now done. The other part, or the other thing I will do, I will calculate the current going here. This current minus this current is equal to this current. Remember now, if I calculate this current and I calculate this Vm over this current will give me the value of this resistance. That's the style. So look here, Vm equal to Rm, which equal to 100 millivolt. He means this voltage, 100 millivolt. This is 100 millivolt. Done. Is equal to 1 or I total minus Im. That means 1 minus 100 microampere. This is 1 ampere. And this is 100 microampere. Subtract them, you are going to get the current here at this location, which equal to 999.9 milliampere. Now I have this current and I have this voltage. The voltage over the current is equal to the required resistance. Remember, don't approximate. You see the value is very small, but don't approximate. 0.1001 supposed to be kept as it is. So by connecting this resistance in parallel with the PMMC, we will be able to measure 1 ampere.